Now on to electron configurations. This will probably take more than one video, so I crave your indulgence as I figure out breaking points. But electron configurations are essentially your roadmap to various and sundry electrons within a given atom. This follows Schrodinger's model of the atom, if you know anything about the history of how the model of the atom was developed. And Schrodinger said that electrons were not on specific orbits around a nucleus, but instead were located in areas of highest probability, three-dimensional shapes, where electrons could be found on each level of the atom. So we had four different levels, if you will, or four different orbitals, excuse me, E, F, four different types of orbitals in which we can place electrons. Again, 3D shapes where I can house these electrons, where they will most likely be. The s orbital is the first type of suite, if you will, where the electrons can hang out. It is shaped like a sphere. I am not an art teacher, so you will have to pardon my beautifully artistic drawings. Shaped like a sphere, I can put two electrons in that sphere. So think of it effectively as a one-roomed suite, the s orbital, rather small. These are the cheap suites. The next type of suite that we can have is a p. This is a lowercase p to represent this type of orbital, and it looks like a dumbbell. Now in space, I have three of these dumbbells. One on the y-axis like this, one on the x-axis, and a third one, which I can't really draw, on the z-axis, so effectively coming out of the board. So three different suites in this p orbital, three different rooms in this p suite. Get my terms right here. I can fit two electrons in each of these rooms for a grand sum total of 6 electrons that can find their home in the p suite. Again, these are three-dimensional shapes in which electrons will be most likely found. Our next one is the D suite. Our D suite has 5 rooms. So we have 4 rooms that look like that 4-leaf clover shape, and then one funny-looking one that's a dumbbell with a donut around the middle. So I have 4 of those. And then one of those guys. So 5 rooms in my D suite in which I can place electrons. 5 rooms, 2 electrons per room means I have 10 electrons that can find their home in the D suite. Last, our penthouse suite is the F orbital. Instead of a 4-leaf clover like this, it's actually a 5-petaled flower. And again, I know I'm not drawing these on the pretty little x and y axis. This is just to give you an idea of the shape. So I have these flowers. That's usually how the F orbital is described, a 5-petaled flower. So 7 rooms in my F suite, 7 times 2 electrons per room, gives me a grand sum total of 14 electrons. And again, yes, I know there are better ways to draw these shapes. I'm just trying to give you a vague idea of what they look like. This is basic chemistry after all. So these are all places where these electrons can be found. And our atom has multiple rings where we can place these electrons. First ring, second ring, third ring, fourth ring. Those rings, luckily enough, also correspond to the rows on the periodic table. So if you're familiar with the table, you can actually read an entire electron configuration with just that. That's all you need. So if an electron is on the first ring, or the second ring, or the third ring, we can use our periodic table as a roadmap. We just have to pretend like it's blank, that the only box that is filled is the element that we're talking about. A shortcut real quick, we can use the sections on the periodic table to represent those orbitals we just talked about. So when I start placing my electrons in their different rooms on their different levels, I can use the periodic table as a shortcut to figuring those out. So anytime I'm talking about these first 2 columns here, these first 2 groups, This represents electrons placed in the s suite. So if the electron was placed here, that would be on the first ring in the s suite. Here would be on the second ring in the s orbital, third ring, fourth ring, so on and so forth. This section over here, these 6 groups, represent the p suite. We said 6 electrons could go in the p suite. 1, 2, 3, 4, 5, 6. 6 electrons that can go in my p suite. Slight mistake. Helium's actually part of the s. My apologies. So we have S, P. This middle section here, my transition metals, we'll do them in a different color. My transition metals represent my D suite. We said 10 electrons could go in the D suite. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons in the D suite. Now D's do something funny. When you're on the 4th row, but you're in the D orbital, this is not actually 4D. This is actually 3D. D's drop 1 from whatever level you're on. This is thanks to something called the off-bow principle, which we will discuss in the following video. For now, just take my word for it. D's drop 1. Our last group, our pentose suite that we talked about, is down here, my lanthanide and actinide series. This section down here, these are my F's. 14 electrons in the F suite, 14 electrons across. Depending on the periodic table you have to be careful. Lanthanum and actinium, lanthanum anyway, they belong up here in the D block. So if they're tacked on the front of your F block here, they are not F's. They actually belong in the D section. It just depends on the table that you're using. F's are screwy, kind of like the D's. This is not, in fact, 6F. This is 4F. Again, thanks to a quirk of energetics, so which level is filled in which order, which again is the off-bow principle, which we will discuss in the following video. So this is just a shortcut, so have this in mind. In the next video, we'll discuss the principles necessary to construct an electron configuration using these wonderful shortcuts and the principles I mentioned before. See you next time.